Hey everybody, I'm sorry for the discontinuation of the first video. Uh, I didn't mean to cut it off right in the middle of this exercise, but now we're going to pick up where we left off. We have the thing that we're trying to maximize, the area, expressed as a function of one variable, x. And we go to step 3. Determine the restrictions on the independent variable, and usually that's x. Now, what this means in this step is that we're trying to figure out if there's any limitation as to how large x can be or how small x can be. And think about it. X is the length of half of this side. So 2x is the length of this side. What's the smallest that x could be? And we'll keep it real. We won't suppose anything that's not possible, like x is negative 10 feet or anything like that. But we will allow ourselves to assume anything that's possible, even if it sounds somewhat absurd. So let's see, 2x is the length of this side. What's the smallest that we could make the length of this side? We could make it 0, couldn't we? And if the length of this side is 0, that means that x is 0 too. And so in that case, here's what the pen is going to look like. We don't have any fence here, but we have these 3 pieces of length y laid right one on top of the other like this. So we have a pen of length x equals 0 and width y. It's not the smartest thing in the world to do, but we could do it, right? We're certainly not going to enclose a maximum area that way, but we could do it, couldn't we? We could actually let x be 0. So I'm going to write that down. X could be as small as 0 feet. Not the smartest thing in the world for me to do, but I could do it. And that is the smallest that x could be. X can't be any smaller than 0 because x is a length, and we don't have negative length, do we? Okay. Let's take it to the other extreme. What's the largest that x could be? And to make this x as large as possible, I could use all 300 feet of my fence on this one side and not save any for these 3 pieces of length y. So I could use all 300 feet of fence on this one side, and this one side is of length 2x, so that means 2x is 300 feet, so x is 150 feet. X could be as large as 150 feet. And what that would mean is these 3 sides of length y wouldn't exist. My fence would consist solely of these 2 pieces of length x, and this is what my pen would look like. My pen would consist of a piece of fence of length 2x, and the width would be 0. This distance would be 300 feet. The width would be 0. The enclosed area would be 0. Not a very smart thing for me to do, but I could do it. Now, why am I willing to let things go to such absurd extremes here? Letting x equal 0 feet, letting x equal 150 feet. We'll see why in the next step. Step 4. Maximize or minimize using the techniques of calculus. You know, it sure would be nice if I could use the absolute maximum minimum value test, because all I'd have to do is find the critical numbers and then take the critical numbers and the endpoints and plug them into the original function, and I'm done. So I guess it would be prudent for me to see if I can use the absolute maximum minimum value test. So let's see. Is A of x continuous? Well, here's A of x, and essentially it's a polynomial. And polynomials are continuous. So yeah. Is A restricted to an interval that's closed and finite? Well, here's the interval right here. X is between 0 feet and 150 feet, and X can equal either of the endpoints. Here's the interval, 0 feet, 150 feet. And this is part of the reason why I carried things to such absurd extremes. I want to be able to use this absolute max-min value test. So I want my function to be restricted to a closed interval of finite length. Now, third thing, is the interval finite? Yeah. This isn't negative infinity and this isn't positive infinity. That interval is finite. Since we answered yes to all 3 questions, this means that we can use the absolute max-min value test. And this makes us very happy because this is easy. Find the critical numbers, and then take the critical numbers and the 2 endpoints, plug them into the original function, and we're done. What could be easier? Okay, so part 1. Find the critical numbers. And to do that, we have to compute the derivative. Now we're looking at this thing and we're probably thinking, wait a minute, what are we going to do with this 200 feet here? That we've never computed the derivative of a function that had feet in it. Well, let me ask you something. What is a foot? No, I'm serious. What is a foot? And you'll probably say, oh, it's 12 inches. And I'd say, you're absolutely right. And then I'd say, is a foot ever 11 inches? And you'd say, oh no. And then I'd say, is a foot ever 13 inches? No, no, it's always 12 inches. Well, if a foot is always 12 inches, then a foot is a constant. All this is a constant, just like 4/3 is a constant. And when we compute the derivative, we treat this the same way we treat any other constant. So a prime of x, we have a constant times x, and we compute the derivative. That's just the constant, 200 feet. 4/3 x squared, the derivative is 8/3 x. And we're looking for type A critical numbers. A prime of c equals 0. So we set the derivative to 0. And we solve for x. So let's see. We have 200 feet equals positive 8/3 x. And then we divide by 8. Let's see, 200 divided by 8 is 25, isn't it? And then we multiply by 3, so that's 75 feet equals x. Critical number. And then we look for type B. A prime of c, undefined. Here's our derivative. 200 feet times x minus 4/3 times x squared, multiplication, subtraction, multiplication, exponentiation. We're dividing by 3 here, but that's not going to give us anything undefined. So there's no type B critical number here. Okay. So we've got the only critical number. Now, on to step 2. Plug the endpoints and the critical numbers into the original function. Here's the original function right here. So, one of the endpoints is 0 feet. So I have 200 feet times x, or 200 feet times 0 feet, minus 4/3 times x squared, well, I have 200 times 0 is 0. I have feet times feet is feet squared. So this is 0 feet squared minus 4/3 times 0 feet squared. 0 feet squared. This is the area that we enclose when we let x equal 0. But we knew it was going to turn out that way, didn't we? So we plugged in the left endpoint. Let's plug in the critical number now, 75 feet. 200 feet times x, which is 75 feet, minus 4/3 times x, 75 feet squared. Okay, let's see. This is 4 times 75. Tell you what, 2 times 75 times 75. 2 times 2 times 75 times 75. Well, let's see. Forgive me, I'm actually going to have to think. Looks like this is going to be 15,000 feet squared. And I have 75 times 75 times 2 times 2. Okay. So let's see, that's 4 times 75 times 25. And 4 times 25 is 100, so this is 7,500. 7,500 square feet. Okay. And then the last one, got to plug in the right endpoint. A of 150 feet, 200 feet times 150 feet, minus 4/3 150 feet squared. And goodness gracious, this looks like 30,000. And let's see, 2 times 150 is 300. So we have 300 times 300 is 90,000, divided by 3 is 30,000. Okay, we get 0 feet squared. What do I do now? I'm using the absolute maximum minimum value test. I've taken the endpoints and the critical numbers and plugged them into the original function, and I find the absolute max and absolute minimum values by inspection. I just look and see which number is the largest. This is absolute max. This is the absolute maximum area that can be enclosed. $7,500 square feet. Now I have an answer, but there's actually a step 5 to this process. And there's a step 5 to this process just for people like me. Because as soon as I get an answer, I go, aha, I've done it. Okay, I'm done. And you know, I never actually look at the original exercise to make sure that I found what it was that I was supposed to find. I get an answer and I just assume that that's what I was looking for. And this is a fault that has plagued me throughout my life. I get an answer and I don't even bother to look at it and say, well, wait a minute, was this what I was supposed to find in the first place? So we'll go to step 5, which essentially is this. Make sure that we've answered the original question. And this step is tailor-made for me because a lot of times I just don't do this. I get an answer and I just automatically assume that this was what I was looking for, even though it's quite possible that I got so involved in the details earlier on that I might have actually forgotten what it was I was actually trying to do. So I need to look at the original question. And the original question was something like this. What should the dimensions of the pen be? Something to the effect of, what should the dimensions of the pen be so that the enclosed area is as large as possible? So we've got the largest area possible, but they're asking for the dimensions. So length equals 2x. And what value of x was it that got me my maximum area? When x is 75 feet, here's our absolute maximum area. Now the length is 2x, so that's 2 times 75 feet, which equals 150 feet. So my length is 150 feet. And what about my width? Well, let's see. I did have 300 feet equals 3y plus 2x, right? And 2x is 150 feet. So that means that this is 3y plus 150 feet. And what that means is that 150 feet equals 3y. And so that means y equals 50 feet. Okay, I got the dimensions of my pen that caused the largest area possible to be enclosed. I've answered the original question. Now I'm done.